Please join me in welcoming Mahnush Movahedi of Definity, Roy Keene, Weiyang Wang of Cortex, Yijia Zhang of Origo, Qiang Li of eNotes, Jae Kwon of Tendermint, and Melanie Marsollier of POA for a panel discussion on consensus mechanisms.
Thank you, everybody, for being here. And we have a very large, excellent panel. And the panel is about consensus mechanism. I give a very short introduction before asking the questions. So consensus mechanism was about Byzantine agreement. First, they introduced in the research area. And the toy problem that they played with was a war problem. So it was a Byzantine agreement. 3 generals wanted to agree on when to attack a city, and one of them is adversarial and bad. And if 2 generals can agree at the exact same time, then they can win. Otherwise, they will lose. This is a problem that is introduced by Leslie Lamport around 35 years ago. So to formalize the problem, there are n nodes. Each start with a bit, and T of these nodes are adversarial, and all other nodes should output the same bit. And if the bit should be equal to one of the honest nodes input. So this is a very interesting area in the research, which kind of has 2 Turing Award winners, Leslie Lamport 2013 and Barbara Liskov 2008. And this is a slide I borrowed from my advisor when he wanted to encourage us to work on the consensus and Byzantine agreement problem. He said, you are going to win a Turing Award. That's a very important problem that shows why this is a very, very important research problem. And now why consensus related to blockchain is that blockchain or Bitcoin essentially is a consensus protocol. So Bitcoin solved the Byzantine agreement problem using proof of work as its leader election mechanism. So now let's look at the blockchain and see why it is related to consensus. So a blockchain is actually an augmented data structure. It's nothing more than a data structure. But what makes blockchain interesting is that on each step, after you add a block, eventually you agree on one block, you agree on one path. So you have blocks and you chain them together, and then after you agree on one block, you actually can agree on the whole path. That is why it is more efficient than agreeing at each step of the protocol. So now let's compare PBFT-based consensus protocols with the blockchain consensus protocols. In the PBFT consensus protocols and blockchain consensus protocols, both of them, the first step is to choose a leader. In blockchain, the leader is randomized, choose randomized using proof of work. But in PBFT-based, they just rotate the leaders. And then after they choose the leader, they propose a value. The leader proposes a value, so everybody can agree on. In blockchain protocols, it's a block. In traditional consensus protocols, it's a value. And then all the parties in the protocol should check if they reach agreement or not. And this check is very expensive for PBFT-based protocols. And but in the blockchain-based protocols, they never check if they reach agreement or not. They just repeat. And since the leader is randomized, at some point, the leader is good and honest, propose one good block, and they reach agreement, and they agree on the whole block. So there is no termination for blockchain protocols. There is no instance instantaneous consistency, but it's an eventual consistency. But for PBFT-based protocol, they reach agreement at the same time. It's an instantaneous agreement. So the key observation here is that we can have different mechanisms for consensus protocols with its goods and bads, and the blockchain is a series of agreement on the protocol. So blockchain is essentially a series of consensus protocols. And we can amortize the cost by using agree on once in a while. Instead of agreeing on each block, by agreeing once in a while, we can amortize the cost and have better efficiency. So now here I'm with my panel to talk about consensus protocols. So the first question I want to ask is that in research area, we know what is consensus. But in industry, a lot of different projects use consensus protocol or consensus mechanism to define something more or something different. So I want each person to introduce himself, introduce the company, and talk about what's the meaning of consensus in your mind. Okay, Jay, do you want to introduce yourself?
Sure, hi. I'm Jae Kwon, and I'm here to talk about Tendermint and Cosmos. So I talked about Cosmos earlier, but and I also said that Cosmos was based on Tendermint, the BFT protocol. So when we started Tendermint, it started from a paper published in 1988 by Dwork, Lynch, and Stockmare, and I hadn't discovered the PBFT paper. Or I think I did, and it was too complicated, but the 1988 paper was simpler. So I started from that, and so we share the same definition of consensus, which is deciding on a single value. In our case, it's deciding on what the next block should be, and it goes through a two-phase commit algorithm. The definition of consensus, what you want is both properties of liveness and safety. So liveness means that you're always going to be able to create a block, and safety means that once you've created a block, you're not going to create another one that undoes that one. So there's going to be no fork. Essentially, that's what that means. And there's also the model. You have to consider the model. So Tendermint provides liveness and safety against up to 1/3 of Byzantine actors in the model of the internet, which is like a partially synchronous system, which means that when you have a packet and you want to send it to another machine through the internet, then there's some finite amount of time. You don't know how long it's going to take, but all you know is that that it takes some finite amount of time. So can the network and the blockchain reach consensus with liveness and safety under those circumstances? So that's our definition.
Thanks, Melanie.
So my name is Melanie. I am a validator in the POA network. That's my night job. My day job is I am a consultant for Ernst & Young, and I focus on cryptocurrency consulting. But for the sake of this panel, I'm wearing my POA network hat. In terms of the question, what is a consensus mechanism? I think the panel, we had a little chat earlier thinking this is such a broad question. I think I'm going to talk a bit more about POA later in this panel, but for consensus mechanism itself, I think it's a decision. It's an ideology. So there's different consensus mechanisms that are available, and it comes to a decision of how, well, for a lot of consensus mechanism, how distributed you want your block production to be. And if you want it to be extremely distributed, then you have the case of, for instance, Bitcoin. We can think of Ethereum as well in a way. And then that creates a sovereign grade censorship resistance platform, which is great, and it's very useful, and it's needed. But not every platform needs to be at that sovereign grade censorship resistance level. And some platform can be at a platform grade censorship resistance level. And those projects, I think, service a need that your Bitcoin or Ethereum services less. And through doing that trade-off, you reach more scalability. You can be very innovative in the way that you approach your consensus mechanism. So I think those are all great innovation that are possible if you kind of move a bit away from this sovereign state level and explore the platform grade censorship resistance level.
Okay, thanks.
Hi everyone, my name is Weiyang. I'm from Cortex Labs project. We just bring AI inference computation onto the blockchain. So talking about consensus on AI blockchain, we have a double layer design. The bottom layer is just similar to the traditional POWs, but this kind of POW is more ASIC hard. They are composed by a bunch of ASIC hard algorithm. At the upper layer, so we introduced the idea about AI inference consensus. So this kind of consensus is not about the innovation at the communication part, but at the computation part. So think about an ordinary hash function called SHA-256. You always have the same, when you have the same input, you always have the same output. How can you ensure the same thing happens on the AI inference? So when we have AI models, deep learning models like convolutional neural network models, we have many flow number computations. How can we ensure when we have the same image, we always get the same output? The core idea is called quantization. Basically, it is a model compression technique, but when using AI model compression, it can also bring this kind of consensus. So many people may wonder that whether quantization, when you change your flow number AI models to 2-bit bit width AI models, can the accuracy be kept? But it's very lucky. It's very easy to achieve that. Not much accuracy is lost. So that's the main idea about AI consensus in Cortex Labs project. Thank you.
Roy.
My name is Roy Keene. I'm with the Nano project, and we use a delegated proof-of-stake consensus model where stakeholders elect representatives to vote on their behalf to reach agreement about transactions on the blockchain with a Nano, and Nano's a much more simple project relative to most of the other ones where we're just trying to transfer value from one stakeholder to another, one user to another. And so we can achieve consensus temporally very quickly, and to do that all pretty much instantaneously on our highly connected network among all the peers.
Thank you, Roy. Chen.
My name is Qiang Li. We're two heads here. I'm advisor for eNodes, and also I'm a chief scientist at Cloud Minds Technology. We actually, two teams work very closely in various capacities. So we use blockchains mainly to support what we call cloud AI and the cloud robotics platform. Our vision is that in the next 10 years or so, we'll have a lot of service robot at home and at different places, and we are positioned to be a operator, just like the operator operate your mobile phone today. So what we're facing is the identity management and security for the entire platform. The scenario we run into is if you have a robot at home and another robot knocks the door, says, I'm picking up your package. And so far today, there's no way they identify each other unless it's come from the same company. So we use blockchain for identity management, hoping to set a platform for IoT robotics applications. The consensus algorithm we use is something we call legitimate POW. So it's basically POW consensus, but we don't want to burn all the electricities. So what we do is that the minor node, they are regular computers, but the hash is calculated by a hardware unit. We call it equalizer. And the hash is calculated and signed by the private key burned into that unit. So only those with the correct sign will be accepted. So it becomes very easy to understand the consensus algorithm, very easy to prove its correctness, and we don't have to worry about 51% attack. So we have already implemented that for using that blockchain platform to implement something called the software-defined perimeter. It's defined by computer cloud security alliance to protect our network and also our cloud. Yeah.
Thank you.
Okay, so this is Yijia from Origo. So we're trying to bring the privacy-preserving smart contracts to the blockchain. So it's more like when you can do voting and you can do auction on current Ethereum. And but after the voting, after the commitment or after the seal open, then all of your votes or all of your bidding price will be public. And so to us, it's like the consensus is like a group of people need to make agreement on a proposal. And then the problem is like you achieve the privacy. It's more like you cannot only do the calculation just on chain. You have to, because if you do everything on chain, then things gonna be public. Then you need to do some stuff off chain. The problem is like, okay, the computation is done by someone else, not by the people on chain. And how do I trust? Because that could be dishonest, and that could be a wrong calculation. And then how can I make sure that it's correct? So we're using a crypto tool named like a zero-knowledge proof. It offers a proof to say, okay, it's definitely, if I verify that proof, everybody can verify that proof. You can prove that this calculation is definitely correct. Second, it also proves it's a zero knowledge. So it's more like there's no information leaking from this computation. So in this way, it's like people can challenge it or like can do this kind of stuff and can challenge whether your calculation is not correct off-chain, but when you verify it on-chain, you're going to make an agreement to say, okay, this is correct. So this calculation is a little cost than normal calculation. So we did some like improvement on consensus. We use a hybrid consensus model. So it's more like we use a POS as a base to mine some to validate or choose a group of like identity blocks. So for example, we choose like several hundreds people. And then we run a PBFT based on that. That will be, because if you run PBFT on a bunch of like all of the whole network, then the latency, all of the issue will make it pretty slow. But if you like running a PBFT on a selected group of people, then it will be much faster. So this is like a hybrid model. I think Definity and like Zilliqa, lots of like other projects also like using similar ideas. And it also can guarantee this kind of like fairness, like everybody has the same chance to actually get chosen. Yeah, so that's probably the
Okay, thank you. So the consensus mechanism was around about 35 years. So why we are still in the research and development stage? So what is very difficult? What is inherently very difficult? And how we can achieve better efficiency is a very good question to ask. I want to ask you that what are your company is doing? What is your protocol is doing to achieve better efficiency? For example, do you do sharding, proof of authority, and can you talk about how you achieve better efficiency using your protocol? So you want to move around? maybe we can start this time with Melanie. Do you want to talk about more on proof of authority and how proof of authority is more efficient than usual proof of work or proof of stake protocols?
For sure. And I realize as well that everyone on the panel kind of explained their consensus mechanism, so we can probably just skip the question about proof of authority and I can explain it quickly. So you can follow me, guys. So proof of authority, I think the best way to think about it is to compare it to proof of stake. And proof of stake, for those who are not familiar with it, is, okay, well, if I stake or if I put aside an amount of tokens, so for instance, 100,000 ethers, then I am incentivized as a validator to act in accordance with the interests of the network. That is definitely a good idea and a very interesting approach. However, POA is thinking, well, if 100,000 ether or tokens is a small amount of token for me, then maybe I won't mind kind of burning through those tokens and still acting not in accordance with the interests of the network. Now, what can we stake that means the same for everyone? And I think we can say that your identity, your reputation is something that everyone or most people attribute a similar value to, and it's something that is very important for most people. So POA asks their validator to stake their identity, and the principle is like, my reputation, my identity is important, and I don't want to be associated to bad behavior. So I have a public notary license in the state of California. I've staked my identity, so my address is public, my name is public, and then I'm incentivized to act in accordance with the network. So back to the question. The question being scalability and
achieving
efficiency.
efficiency.
Sorry for that. So we're currently 17 core validators on our mainnet, and we're trying to we're wrapping up, and we're going to be 25 validators on the mainnet. So it is a decent-sized validator group, and because we're 25 validators, we get to be able to be more scalable than platform like Ethereum and Bitcoin, where we don't have the network latency is smaller just because of the validator set group. In terms of R&D, I think we definitely value R&D a lot, and there's some people proposing that validators, some of the reward, the block reward that we're getting, we put it aside in a little like guinea pig or like pot, where we're gonna give to the R&D team or to research people like universities, and have them kind of work with us and experiment on way to be even better at what we're doing. So R&D is definitely a very important aspect of POA, and we're trying to continuously upgrade our network.
Thanks. So to achieve efficiency, Cortex has a different idea. So I think what you do is to specialize the consensus protocol for a specific use case, like AI use case. So I think AI is very computation and data heavy. Do you think it's the best use case to make sure that you can achieve consistency on? What is the property of the AI protocols that like you find interesting to work on?
So you may heard about the stories earlier this year that if you want to deploy our AI models, like on AWS, earlier this year there are stories about Google's DNS contamination and DDoS on AWS and hacking events on AWS. So in the world, then you cannot trust, and in a blockchain world, you cannot trust anyone. You must ensure the correct node is executing your AI model, inference correctly to avoid AI malware or AI malfunction. You have to ensure the same image input is input to your AI model. You will always get the same output. So that's the core value of Cortex consensus. And that's it.
Thanks. So Roy, I think your protocol is DAG-based. Can you define what is the difference between DAG-based and blockchain-based protocol?
Yeah, the DAG is just a directed acyclical graph, which just means it's many blockchains. Each individual account has its own blockchain. And so as it relates to consensus and just reaching agreement on what the current state of that chain is, it's a lot more efficient with each individual user only issuing changes and sends and receive blocks on their own account. And so we're able to just to make pretty much instantaneous agreements and on what that account's actual state is.
Okay, so usually DAG-based protocols cannot provide total ordering because if you assume an account-based protocol, then usually they provide ordering on the accounts. Is it the same thing for you? Or?
Because it's a blockchain per account, the DAG is actually a segregated part of it, where sends on one account relate to potential receives on another account, which is where the actual graph in the directed acyclical graph occurs. But that receive block is up to the receiver to generate asynchronously at any time in the future or never, if they so choose, so that the receiver or the account holder or the stakeholder, however you want to view it, actually owns their chain and is responsible for ordering it and making sure that the activity they want to occur on it does actually occur. So.
Thanks. Sorry. I also like to talk about privacy preserving and consensus. So here, two of our companies are doing privacy preserving protocols, and they need to achieve consensus on the privacy preserving. And so do you have any challenge to maintain privacy while achieving consensus and agreement? So was it a main challenge for eNote or was not?
Yes, that's an issue we're dealing all the time. So our approach basically create a sidechain, and so the data is visible within the sidechain, but it's registered on the big chain. That's how we handle the privacy issues. Yeah.
And the same question goes to.
Okay. For us, it's like so the problem is like on a blockchain, not all of the requirements actually need privacy preserving. Some are need and some are not. And so you don't want all of the infrastructure is the same for all of the validators or all of the mining nodes. So to reach a consensus, usually the limitation is limited by the slowest node. And so for doing a private preserving verification, usually you need to verify the proof is whether correct or not. This kind of calculation could be slower than, could be a little slower than the normal calculation. And then you don't want this kind of calculation ruin the other normal computation. And it's pretty interesting to our stuff. It's like if you want to public, then all of your data will be stored on chain, similar to Ethereum, and then you do calculation, then definitely there'll be no problem. And then if you do private preserving, then your data is not on chain, and then or we'll buy an encrypted version, and then actually different model. So it's pretty easy for us to do a simply computation sharding because it's not based on the state. Because if you want to do public or do the private, they are not sharing the same state. So usually don't have this kind of state dependency. So we use like a sharding to actually help this. So it's more like we can have a several shard only for verified. It's like a private preserving stuff, and also we can enable the other shards, other shards for the public. Then it doesn't like, so the slow calculation doesn't affect the public ones a lot. Yeah.
Okay. So I'm glad that you bring up sharding. Sharding is one of the methods that can make the consensus protocol very efficient. And I think Cosmos has some ideas to use Cosmos on top of the Tendermint can consider be as a sharding protocol. Maybe Jay can help us more on describing how they achieve more efficiency using sharding and Cosmos.
Okay. So I want to start with, I guess, the Tendermint part. So before sharding, about how Tendermint achieves fast consensus. So there's a proof from a while ago that says that if you want to have more than 1/3 of Byzantine fault tolerance in a partially synchronous network, then you need to have 2 rounds of communication to achieve consensus. So okay, that already tells us that we need to limit the number of signers in order to achieve fast block finality. So the Cosmos network, which is going to launch pretty soon, it's going to have 100 validators, and that's going to result in around 5-second block times. So every block comes around every 5 seconds or so, and each block is final. So you don't have to wait for additional confirmation. So it's really fast. All right, so that's optimum vertical efficiency of a consensus algorithm. You can't get much faster than that, right? There's little things you can tweak, but in terms of big O notation, this is it. So if you need, so that gives you the ability to have a global blockchain with 5-second block times, or a localized blockchain, say in Wall Street, and you can have sub-second block times, right? But you're going to need more blockchains eventually, because each chain is kind of throughput limited by the Merkle tree of the persistent state. So you can only have, for a single blockchain, if you want a blockchain to be something that your laptop can sync with, right? Because that's what makes it transparent, auditable, and accessible. Then you can only handle 100 transactions per second or so, due to the limitations of the persistent Merkle tree, which is inefficient, more inefficient than traditional databases, although that can get better too. And so the way Cosmos handles this is it scales blockchains horizontally by allowing many blockchains that run in parallel, each with their own logic, with their own virtual machine or their own smart contract application. And then there's a hub that connects many of these chains together. And the way the chains communicate with each other is through proving that the other blockchain committed this block. And you can do that very efficiently with a BFT algorithm like Tendermint, because all you need is 2/3 of signatures that prove that the validators of that other chain signed off on something. So the Cosmos hub is a hub where many spokes are other blockchains, and you can have shared security where maybe the same validator set is running a rack of servers and validating on many simultaneous chains under the same umbrella. Or you can have sovereign blockchains with completely independent validator sets connecting, and you can get interoperability through the hub, because now you can pass tokens between blockchains. And this allows you to have, your CryptoKitties blockchain over here and your Zcash blockchain over there, and you can move your tokens from one blockchain to another and use whatever functionality you need.
Thank you. So, but what happens if you want to do atomic transactions? Like if I want to book a flight and hotel at the same time, but not, if one goes through, the other one should go through, but if the first one didn't go through, the second one shouldn't go through too. So do you have Cosmos has any idea on how to achieve atomic transactions and consistency?
Yeah, okay. So I think in that case, still atomic cross-chain transactions and hash lock reveal systems work fine. So you can still do that. But another way might be, of course, if it's on the same blockchain, then you can just have the framework handle multiple simultaneous messages.
It's very easy for the same blockchain. It's more difficult when you have sharding.
So here's another thing you can do. You could create another kind of hub. It's not it's, maybe it's going to be logic we might add to the Cosmos Hub, but it can be like a condition, a lock condition, and you can have other blockchains communicate that certain conditions have been satisfied, and then other blockchains that read from it. So this is something we can build on top as long as we have a protocol for blockchain communication, like TCP/IP for inter-blockchain communication. That's what Cosmos is about.
Okay, thank you. People and humans are not the only species who decided to achieve consensus. Consensus is usual among animals as well. Bees can achieve consensus when they search for a new house, and ants can achieve consensus when they search for a new house too. To kind of talk more about artificial intelligence and consensus, I like to know more about your ideas of how you think about looking at the nature and looking at the protocols that are in the nature to see if we can achieve consensus using their algorithms. Who wants to start?
Yeah.
Okay, Roy.
Okay, yeah, so there's a property called emergence where less capable units of like ants or bees work together and solve complex tasks without any coordination. Each one is following a relatively simple program and they're all pretty deterministic, but together they can emerge into a more intelligent system that's a complete unit doing cooperative things, seemingly without any coordination. And the mechanism that is most likely to be utilized in this is consensus, where they're all agreeing locally to create a global intelligence and making global decisions by making local ones that propagate out. So there's a lot that we can see looking at nature and the fundamental property of emergence, where our intelligence is the result of billions and trillions of cells working together to make us an intelligent being somehow, and ultimately it's due to the property of consensus. So the more research that's done into consensus and understanding what that means for that in the field of artificial intelligence, we can start to progress into building even more complex systems that emerge from simpler systems, just like ants and bees.
Okay. Thank you. So I think we are very close to run out of time. I want to give our speakers to have any thought that you want to share or any announcement that you want to have to the public. Let's go around and see if you have any announcement.
Sure. So Tendermint's been in development for a long time, and we're about to launch a test in the Cosmos Hub, and in doing so, we need to have testnets to practice launching chain. And there's currently a testnet going on now with the actual staking code. So if you want to become a validator, I highly encourage you to look into it, because there's going to be 100 validators, and this is going to be the new kind of mining business, right? So anyone can get into it, because proof of stake really hasn't arrived yet in the full picture of what's about to come, and now's a good time to get started. So join our testnet, go to cosmos.network. Thanks.
Okay, Melanie.
I think my first message is very similar to yours, Jay. Same thing, POA, we are still recruiting for validators. And the way to do it is to have a public notary license in the state where you live. And it's quite straightforward. You can find more information on our GitHub. So encourage everyone to look into it, especially if you are from another state in California. I think California is very represented, but I think we need a bit more representation from other states. And then I think second announcement, my colleague Igor will be presenting the POA bridge tomorrow. And I think we did a very good job with the POA bridge. I think it's one of the first of its kind in being able to achieve what we're achieving. So very interesting stuff happening. So highly encourage you to show up tomorrow and listen to Igor presenting about the bridge.
Thank you.
People may wonder what's the first decentralized app suitable for Cortex. Just think about your cold wallet. You do not have to trust any cold wallet manufacturers, but you can trust Cortex to implement your human face recognition algorithm and voice recognition algorithm using Cortex Labs.
Okay,
Thank you.
Yeah, Nano's been around and operational for quite a while, so most of our announcements are just routine. We've recently done a release which will release 14, which will release, which will improve the efficiency of actually our consensus mechanism due to some voting issues that we've resolved. Other than that, you know, consensus is an interesting topic, and I'd just like to get questions from you guys later.
Based on the legitimate POW scheme, and we are building a platform we call ID of Things. So it's basically provide a generic ID platform. And for people working on IoT and the robotics, we welcome collaboration on that.
Thank you.
Okay, so Origo currently are building a proof of concept based on Ethereum. Given Ethereum doesn't have private transaction, but think about auction, because currently we are doing a proof of concept that we can guarantee this kind of auction when the auction is when it's in the beginning of the auction, in the process of the auction, it's fairness, and then at the end of the auction, all of the bid price will be hidden. So this is not achievable on current Ethereum, but we achieved that by running a zero-knowledge proof on current Ethereum network. So we're gonna share this stuff next month. Yeah.
Thank you very much. Thank you very much, everybody, and thank you for listening.